This is lesson 1 in chapter 13, vibrations and waves. We're going to be setting the stage for a chapter on sound and indirectly talking about some of the basic ideas behind the electromagnetic spectrum, which we'll cover later. Periodic motion is motion that occurs over and over again. Periodic means that there is a period of time for an event to take place, for an oscillation or a vibration or some kind of event. And when you have some of the examples of this would be sound waves and water waves and seismic waves and electromagnetic waves. The period, of course, is the amount of time it takes for that entire event to take place. So there are a large number of physical systems that can be successfully modeled with the idea that the force is proportional to the displacement of the medium. And we're going to codify that into an equation and then look at variations of that. Now, Hooke's law is something that we introduced way back in chapter 5. And again, Robert Hooke was a polymath. He had his hands, or at least his mind, on all kinds of things having to go on with science, everything from fossils to microorganisms. He had a brief time where, because of finances and opportunity, he did artwork and learned how to make very, very good drawings, which we have today. He really helped us to develop the theory of cells being the component out of which living things are made. He was an assistant to Robert Boyle, who was a Christian. His father was an Anglican priest, as were his uncles. And so even though he didn't talk an awful lot about his faith, there are a number of quotes where he does talk about the design and the beauty in creation. A not so nice thing about Robert Hooke is he didn't get along very well with Isaac Newton, but not a whole lot of people did. And it's kind of sad to look back in history at two people with Christian backgrounds and to some extent Christian testimonies who were unable to be at peace with each other. In any case, when we look at Hooke's law, you can see it right here. And you might remember that what we're saying here is that a force, represented by the letter F, is going to act on something like a spring, for example, in this case, that's going to cause it to stretch some distance x. And the proportionality constant is k. But you'll notice the negative sign here, because the force is always going to be moving or pulling the object back in the direction from which it was displaced or distorted. So if I exert a force and something moves in this direction, let's call that the positive direction. The force, in this case, let's say a spring, a force acting on a spring, is going to try to pull it back in the opposite direction, which is going to be the negative direction, and hence the negative sign. Remember that K is a spring constant, and it can be very, very, very small, 0.000 whatever. So let's say for the spring that might make the ink cartridge go up and down in a spring-loaded ink pen, or it can be really, really gigantic in the thousands or hundreds of thousands even for cars and trucks. This is called Hooke's law. And over here is where it mentions why we have the negative sign, because you're going in the opposite direction from the displacement. We call this the restoring force. The restoring force. And it can push or pull depending upon the distortion to the spring. So here we have a picture of a spring on a horizontal surface, and we can move the mass that's attached to the end of the spring towards the right in the positive direction, in which case the restoring force is going to want to pull it back in the opposite direction. And the greater the force, the greater the value of x is going to be. We can also have some equilibrium position where x is equal to 0, where there is no force acting on the mass that's going to pull it or extend it one way or the other. So here you have the spring being extended or stretched out. Here you have the spring being compressed. In this case, back up here, the spring is going to pull the mass back, and down here, the spring is going to push the mass to the right. And if we let this thing oscillate, it's going to go back and forth and back and forth. If the surface right here between the mass and the surface on which the mass is resting, if that were possible to be a frictionless surface, your graph might look something like this. Go back and forth and back and forth. But of course, we know that there's going to be friction there. So in the real world, you're going to have something that's going to have a bigger amplitude and then a smaller amplitude and then eventually go to 0. And as this amplitude gets smaller and smaller and smaller, eventually it goes to 0, and we call that damping. And this is going to be mentioned later on. This motion, the back and forth or up and down, is called simple harmonic motion. And it can be with a horizontal spring or it can be with a vertical spring. And so we have our vocabulary words. The amplitude depends upon how much it's bouncing vertically or how much it's oscillating back and forth horizontally. That's the amplitude. And in the absence of friction, you have your simple harmonic motion where it oscillates back and forth between a maximum and a minimum value, represented by the letter A. And A would not diminish if there were no friction. The period, capital T, is the total amount of time it takes to go down and back. One complete oscillation. Notice it's not to be confused with the lowercase t, which is generic for time. Capital T is a specific use of time for one complete event. And then you have your frequency represented by lowercase f, and this is very important, something you'd be expected to know on a test, that frequency is the reciprocal of the period and vice versa. Coming down to this equation here, if we know that F equals ma, Newton's second law, and Hooke's law is F equals negative kx, and so in this very relationship you see that Robert Hooke and Isaac Newton not only had a relationship because they were contemporaries in time, but they also have a relationship in two of their most famous equations. And when we solve this equation for A by dividing both sides by m, we get this equation here, which means that we can calculate the acceleration of some mass based upon its displacement if we know the spring value constant k. And we call this a harmonic oscillator equation because it gives the acceleration as some function of position x. Now, of course, we're talking about an ideal spring. An ideal spring is not going to have any internal friction that's going to cause that amplitude to diminish, but in a real world, of course, there's going to be some heat loss into that spring. So if we look at a simple math problem here, this is not a difficult problem because all we're going to be doing is plugging we have our mass up here, 0.350 kilograms, and we have our force constant for the spring, our spring constant. Remember, the units of the spring constant are newtons per meter. And we're going to, and if we stretch this spring some distance, 1/10 of a meter, you can see that this is a simple plug and chug equation, and right here. And then we can also calculate the acceleration because we have our force and our mass, and the acceleration is going to be negative 37.1 meters per second squared. One thing you should notice down here from this table is that the initial position is halved, then the force and acceleration are also halved. You double the amount of that you're stretching the spring or compressing the spring. That's going to take twice the force, and it's going to give you twice the acceleration. Here is another problem, and this time we have a vertical spring. And again, the more you stretch the spring vertically, the greater is going to be the force. It's going to want to pull it back. Notice that we can take a second identical spring, and that over here we have our two springs in parallel. They are parallel to each other. Later on, when we get to electricity, we'll talk about a circuit where you might have a resistor and another resistor that are in parallel with each other. So get used to this word parallel, as opposed to two resistors in series or two springs in series. And so when you add a second identical spring, you can see that the amount of restoring force is going to be changed. And so if we look at the rest of the math problem here, in the first part, we're finding the value of the spring constant if the spring is displaced 2 centimeters and we have a mass of 0.55 kilograms. In order to create the force, we've got to multiply 0.55 by 9.8 to get the force, because in this case we're talking about the weight of the spring. And here's my distance, and notice it's been converted to meters from centimeters. Then we can take this value that we get for the spring constant, and we can use it in part B down here. And here, if we have a second identical spring that's in parallel, that's where this number 2 comes from. Now we can solve for the new distance that is going to be stretched. And you can see that this distance is half of this distance right up there, because we have two springs that are sharing the load, if you will. And then if we take this value down to problem number 3, what is the effective spring constant of the two springs acting as one? And the effective spring constant then, if this is the distance that both springs are stretched, each about a centimeter, each a centimeter, you can see that my spring constant here is now doubled what it used to be, the effective spring constant of the two springs acting in parallel. And down here they talk about parallel and in series. All right, let's talk a little bit about elastic potential energy. Potential energy that's stored in something that is elastic, which means it can stretch, such as a spring or a rubber band. Rubber bands, we don't think about energy stored in them when they are compressed, but springs, energy can be stored in them when they are compressed. So remember what the formula for potential energy is. If it's gravitational potential energy, we talk about mgh. But if it's potential energy stored in a spring, it's 1/2 kx squared. Because as you stretch the spring more and more and more, it's going to take more and more and more force. Your force is not constant. The force to stretch this distance is going to be twice the force just to stretch this distance if we're talking about some distance x. So if F equals negative kx, and when we stretch it even more, we're going to get twice the amount of force that's going to have to be exerted, and that's going to increase my potential energy. And you recall that we had this back in chapter 5, that the potential energy stored in a spring that is being stretched is 1/2 kx squared. not to be confused with kinetic energy, which is 1/2 mv squared. And so now in the case of a spring or a system that has a spring, we have our work energy theorem that we had way back in chapter 5 again. And so we can have our kinetic energy, our gravitational potential energy, and our energy stored in a spring initial, and then compare that to what we have that's final. If there is energy loss because of a non-conservative force like friction, then the difference between the two has to be the work done in order to overcome that friction. And so here's a diagram showing a weight that's going to be pushed, or maybe it's sliding along a frictionless surface towards a spring. It makes contact with the spring at this point. It now compresses the spring, and when it comes to a halt, the total amount of energy down here that is stored in that spring potential energy is 1/2 k x squared. And then when we let go of this mass and it begins to move in the opposite direction, all that energy, when it leaves the spring, is now, the block now has it, and that's 1/2 mv squared. So all the potential energy in the spring is converted into kinetic energy of the mass of that block. The total mechanical energy of the system consisting of the block and the spring remains constant. And so during the time that the block is in contact with the spring, it's going to be some potential energy stored in the spring and some kinetic energy of the block. And we had a problem that looked like this way back in an earlier chapter, where a car is coming down an incline. It's going to hit a bumper down here that has a spring behind it. So we have our mgh, some height h, and the mass of the car times gravity. This is the potential energy that the car has. At this point, it's going to be all kinetic energy, 1/2 m velocity squared for the car, assuming that there is no energy loss due to friction. And then when it completely compresses the spring over here, it's going to have 1/2 k x squared. So we could find the velocity at the bottom of the incline if we wanted to. Problem doesn't require that, and we've done that in an earlier chapter. And now all of my potential energy is going to be converted into energy stored in the spring, and we can find the distance which that spring is compressed by solving for x. If we calculate the magnitude of the car's maximum acceleration by the spring, this is part B of the problem. Here's my Newton's second law equaling Hooke's law, and we solve it for A. If we multiply the numerator and the denominator by g, we get this equation right here. mg, of course, is going to be the weight, which I would draw like this, the force of weight of the car, and that gives us this equation right here. So we can plug the numbers into the problem and solve for the acceleration of the car. In this case, it's going to be a deacceleration, going from whatever speed it has at the bottom of the incline to a speed of 0. And then if the compression of the guardrail is only 0.30 meters, find the change in mechanical energy due to friction. We're going to lose some heat energy. And so we can take all the energy that is stored in the spring, and this is the potential energy that we started out with, and the difference in the two has to be the energy that is lost into heat into that spring. We can also talk about velocity as a function of position, where we can say that all the energy stored in my spring is going to be converted into energy of motion of whatever the mass is, the object is that has compressed the spring, plus the energy that is stored in the spring. And we can solve this equation for V, which is what we get right here. Keep in mind that A right here is your maximum possible compression or extension, elongation, and X is the actual at any point in time, while the object, the mass, whatever it is in contact with the spring. So if we look at a math problem here, we have a half-kilogram object. It's connected to a light spring, and of course light means we're going to ignore the mass of the spring. We have the proverbial frictionless horizontal surface. So again, this is an idealized circumstance or situation. We take our work energy theorem, and we recognize that all of my energy stored in the spring can be calculated with 1/2, here's my spring constant, and then here is my maximum extension A squared. Then we can take that value right here, and we can come down to the next part of the problem. Using conservation of energy, we can find the speed of the block, the speed of the object, whatever it is, where all of my energy stored in the spring is going to all be converted into kinetic energy, nothing into heat energy, and so we can find the speed of the block. We can also find the velocity of the object when the displacement is 2 centimeters by using the equation we derived earlier, and just plug in my numbers in, and I get my speed at the 2 centimeter mark. Notice this 2 centimeters had to be converted into meters. And then we can compute the kinetic energy and the potential energies at the 2 centimeter position. And so here's my 1/2 mv squared to get my total kinetic energy. And down here we can calculate my total potential energy. And this again is the total potential energy stored in the spring. There's no gravitational potential energy in this problem. So we're going to stop the broadcast right now and pick up with lesson 2 later.